Welcome back to The Explainer. Today, we're diving into something we all do dozens, maybe hundreds of times a day, but rarely think about. We are tracing the literal, microsecond fast journey a web page takes to render right there on your screen. So think about it. What actually happens when you type a URL and hit enter? It feels instant, right? But behind the scenes, imagine a dark, futuristic terminal where that single keystroke triggers this massive, global orchestration. It's a beautifully complex symphony of networking protocols, distributed databases, and heavily optimized rendering engines. Let's peel back the curtain and watch the hidden internet go to work. All right, here's our roadmap for this journey. We're going to cover 1. The keystroke and caches. 2. The global DNS address book. 3. The secure network handshake. 4. The multi-process browser engine. 5. Constructing the DOM and CSSOM. And finally, 6. The final rendering pipeline.
Starting right off with part 1, the keystroke and caches, checking local memory first.
You see, before a single packet of data even leaves your computer, your browser acts a bit like a detective. It checks its local memory first, trying to skip that expensive network trip entirely. There are 2 main ways it does this. First is force cache. This relies on fixed expiration times, using HTTP headers like expires or cache control. It's basically like checking the expiration date on a carton of milk. If the date hasn't passed, the browser just grabs the files straight from your hard drive. Zero network latency. Bam. But what if the time is expired? Well, then we move over to negotiation cache. Using headers like last modified or etag, your browser pings the server and says, hey, has this file changed since I last saw it? If the server sees it's untouched, it sends back a super lightweight 304 response that just tells your browser, yep, go ahead and use that expired cache version. It is such a smart way to save bandwidth before we even truly hit the open web.
Moving on to part 2, the global DNS address book, translating those human-readable names into IP addresses.
Okay, so let's say the local cache has come up entirely empty, or it's your very first time visiting a site. Your browser has to venture out and translate that domain name into an IP address that computers can actually route. Watch how this request bounces through 4 distinct servers. Step 1. We hit the DNS recursor, which is usually maintained by your internet service provider. If it doesn't know the answer, it asks the internet's root name server in step 2. These root servers are kind of like master librarians. They don't know the exact book, but they know which section to check. The top-level domain, or TLD server. That's step 3. The TLD server, say the oneforall.coms, points us to the final stop in step 4, the authoritative name server. This server holds the actual definitive IP address. It's a massive global address book narrowing down the exact street address. And the crazy part? Thanks to heavy caching at the OS and router levels, this globe-spanning lookup almost always finishes in under 100 milliseconds. Absolutely wild.
All right, part 3, the secure network handshake, securing the connection.
So we have our numerical IP address. Now, packets of data have to traverse the internet and lock in a secure encrypted connection. Look at the sheer speed of this timeline. Following that roughly 50 millisecond DNS lookup we just talked about, we spent another 30 milliseconds doing a TCP connect to ensure reliable data transmission. Right after that, we dedicate about 50 milliseconds to the TLS handshake. This is absolutely crucial. It's where cryptographic keys are exchanged to make sure your connection is totally secure and private. Only after all of that, hitting right around the 100 millisecond mark, is the actual HTTP request dispatched. Think about that. All these global network ops and cryptographic handshakes happen in literal fractions of a second before raw bytes even start streaming back to your device. It really is a testament to modern network engineering.
Which brings us to part 4, the multi-process browser engine.
As those raw HTML bytes finally return from the server, we leave the open network and enter the highly secure, compartmentalized factory of your operating system's browser engine. Notice how the networking component operates completely independently from the main browser engine. It funnels incoming data straight into the isolated rendering engine. Inside that engine, you'll spot critical subcomponents, like WebKit handling the HTML and CSS, sitting right alongside the isolated V8 JavaScript interpreter. Modern browsers use this multi-process architecture for a really good reason. If a heavy, clunky script crashes the rendering engine in one tab, it doesn't take down your whole browser, or worse, compromise your underlying operating system. It relies heavily on inter-process communication to keep the user interface snappy while the heavy lifting happens in the background.
Now for part 5, constructing the DOM and CSSOM, building the actual structure. Once the data is securely inside the rendering engine, the browser has to actually make sense of this raw byte stream. The parser acts exactly like a factory assembly line. First, it takes the raw bytes and uses a character encoding, like UTF-8, to convert them into readable characters. Next, a tokenizer breaks those characters down into HTML tokens, figuring out, what's a start tag, what's an end tag, what's text content. Those tokens are then converted into objects, or nodes. And finally, these nodes are linked together based on their parent-child relationships to assemble the full document tree.
And that entire parsing sequence results in the DOM, the Document Object Model. As you can see, the DOM is a tree-shaped, in-memory representation of the HTML document created from the top to the bottom. It's essentially the structural skeleton of the web page. Now here's a fascinating little detail. If the parser hits a script tag while building this tree, DOM construction usually freezes right there until the JavaScript is downloaded and executed. Why? Because that script might dynamically alter the DOM itself. But to keep things moving, modern browsers use a really clever preload scanner that actually peeks ahead in the document to fetch resources like images and scripts in the background, keeping those delays to an absolute minimum.
Meanwhile, simultaneously but completely independently, the browser is parsing your style sheets to build the CSSOM, the CSS object model. This is an independent tree structure representing all the visual styles defined in your CSS. Think of it this way. The DOM represents what is on the page, and the CSSOM dictates how it should look. It calculates the cascading rules for colors, fonts, sizing, basically preparing the paint. And it's crucial to remember that the DOM and the CSSOM are built totally independently. They don't interact at all until the very final phase of the pipeline.
And that leads us to our final stop, Part 6, the final rendering pipeline, painting the pixels.
We've reached the end of the journey, where structure and style finally merge to illuminate the screen. Let's break down these last few steps. In step 1, the rendering engine combines the DOM and CSOM to create a unified render tree. What's super important here is that this render tree only includes visible elements. So if a node is styled with display none, it just gets completely dropped. Boom, gone. Next, in step 2, the engine calculates the layout. It does the math to determine the exact geometry of the page, figuring out exactly where every single paragraph, image, and button needs to sit based on the exact dimensions of your browser window. Finally, step 3, we paint. The browser engine hands these calculated display instructions over to a dedicated GPU process. The GPU rapidly paints these elements into layers, and then, through a process called compositing, it flattens all those layers together to form the final image, turning abstract data into the colored pixels you actually interact with.
It is honestly mind-blowing to think about. This insanely complex symphony, from browser caching and global DNS routing through secure TLS handshakes and down into a multi-process rendering pipeline that translates raw bytes into beautifully painted pixels, it happens billions of times a day, completely invisible to the naked eye. So the very next time you press enter and a page loads instantly, I want you to pause for just a second. Appreciate the microsecond miracle happening right in front of you. Which part of this hidden high-speed journey will you think about next?